Alright, so in the previous lecture, the last thing we did was optimization in functions of two variable. And like a regular optimization problem, you have your target function that you're trying to optimize, and then you have a constraint, right? So if you recall, there was the box problem where we were trying to maximize volume given by xyz under a constraint that the area, which was 2xz plus 2yz plus xy equals 12. Remember, it was an open box that we were trying to maximize. And here, thankfully, we could reduce one of the variable. We could solve for z in terms of x and y and get a function of two variable and just do our partial differential. However, when we move on to higher dimension, in particular three variable, there is a standard method that we use, which is called the method of Lagrange multipliers. So here's what the result says. To find the max or min values of a function of three variable f, x, y, z subject to a constraint. The constraint is given by another function, gxyz equals k. The reason we will have this constant k is it's a constraint, so something is limited by the value k. Then we're going to do two steps. First, we're going to find all values of x, y, z and a constant lambda such that the gradient of the target function is a scalar multiple of the gradient of the constraint function, and the constraint function, of course, is equal to some k, which means it's a level curve of that. Once we have all the values of x, y, and z, we are going to evaluate f at all the points x, y, z from step 1, and the largest is the max value and the smallest is the min value. So we'll look at a couple of examples, including the box one, so that we have results in both. First example, find the extreme values for the function f given by x squared plus 2y squared on the circle x squared plus y squared equals 1. So first of all, you got to identify the constraint. The constraint, of course, is x squared plus y squared equals 1. So in this case, this is a two variable scenario, not three. So it even works for two. But the powerful thing is that it works for more than two as well. Okay, so we start with f. Remember, gradient of f is going to be a vector with x and y component. So that's going to be partial with respect to x and partial with respect to y. And gradient of g is going to be partial with respect to x and partial with respect to y. So what we are solving is this vector 2x 4y is lambda times 2x to y, which means we can compare them component wise. So the first one gives me 2x is 2x lambda and 4y is 2y lambda. Okay, so what does this give me? This gives me 2x, 1 minus lambda equals 0, which has two possibilities. X is 0 or lambda is 1. right? We also have x squared plus y squared equals 1, which is the constraint equation or the level curve. What does this give? This gives 2y, 2 minus lambda equals 0. So y equals 0 and lambda equals 2. So now let's see. If we take the first, if we take x equals 0 and lambda equals 1, right? Then we get 4y equals 2y or y equals 0. Okay, so actually let's use this x equals 0 and lambda equals 1 will give me x squared plus y squared equals 1, so y equals plus minus 1. So x equals 0 gives me y equals negative 1, and if lambda equals 1, then 4y equals 2y, which gives y is 0, and if y is 0, by the same reasoning, x is plus minus 1. So the possible points are when x is 0, y can be positive 1 or negative 1, and when y is 0, x can be positive 1 and negative 1. So we have 4 of these points. And now all we have to do is evaluate this given function at these 4 points. And since our function is just x squared plus 2y squared, this is going to be 0 squared plus 2 1 squared and 0 squared plus 2 negative 1 squared, 1 squared plus 2 0 squared, and negative 1 squared plus 2 0 squared. Okay, so this is where the maximum value occurs. It occurs at x equals 0 and y equals plus minus 1 on the circle, x squared plus y squared equals 1. And the minimum value occurs at y equals 0 and x equals plus minus 1. So again, this is not the maximum minima as we did before, because this is on a particular curve, x squared plus y squared. So what we have is we have a surface and then we have an intersecting level curve, and on that intersection we are finding the maximum and minimum value. So it's not a global max or min. Okay, so let's apply this to the box problem. In the box problem, we were trying to do this under the constraint of 2xz plus 2yz plus xy equals 12. So here we have f xyz is the volume, which is xyz, and the gradient of this, so you take derivatives. Partial with respect to x will give you yz, partial with respect to y will give you xz, and partial with respect to z will give you xy. Then we had the constraint. The constraint is this level curve, 2xz plus 2yz plus xy at 12, but we don't need that because 12 is just a value of k. Partial of this with respect to x will give 2z plus y. With respect to y, the first is a constant, you only have 2z plus x. And with respect to z, the last xy, the derivative is 0, so you're just left with 2x plus 2y. Now solving for this is lambda times del g and the constraint, so 2xz plus 2yz plus xy equals 12. This gives 2xz is lambda times 2z plus y, that's the x component. 2yz is lambda times 2z plus x, that's the y component. And xy is lambda times 2x plus 2y. That's the z component. Now, how do we solve these equations, right? So we need all of these statements to be true. Now, there is no standard method of solving this as such, so we are going to have to do something okay, there's an error here. Del f these are not correct. Del f's don't have 2's, these are just yz, xz, and xy. So the first thing here we can observe is these three are almost the same, right? Almost the same. I can actually make them the same if I multiply by x, if I multiply by y, and if I multiply by z, then my resulting equation becomes xyz equals lambda x 2z plus y, and again xyz equals lambda y 2z plus x, and xyz equals lambda z 2x plus 2y. Now, which means all three of these are the same. So what if I take these first two? So I have lambda 2xz plus xy equals lambda 2yz plus xy. So factoring out lambda, I have 2xz plus xy minus 2yz minus xy equals 0. So I have 2 lambda z x minus y equals 0. So this gives us certain things. Possibly lambda is 0, possibly z is 0, and possibly x equals y. Now if lambda is 0, that doesn't help us, because if lambda is 0, what happens is we get xyz equals 0, and then this is not satisfied, right? So this is not possible. So because this would make x equals y equals 0, and one equation is not satisfied. Now z cannot be 0 because that makes the volume equal to 0. So that is also ignored, which leaves us with x equals y. So that's one of the relations we have. Now I can also compare these two in the same fashion. Then I will have lambda 2yz plus xy equals lambda 2xz plus 2yz. So lambda 2yz plus xy minus 2xz minus 2yz equals 0. Cancel. Same thing happens here. Lambda x y minus 2z equals 0. Again, the same possibilities. Lambda 0, x 0, y 2z. This is not possible, and this is also not possible for the same reason as before. So we get lambda y equals 2z. Okay, now if I use the constraint equation right here with the relations that we have obtained, which is x equals y and y equals 2z, we will now have an equation in one variable. So what would that be? X equals 2z. So let's convert everything into z. So this would be 2zz, and again 2zz, and 2z, 2z. So you get a 4, a 4, a 4. So 12z squared is 12, which gives you z is 1. Again, cannot be negative, which gives you y is 2, and then which gives you x is 2. Now, if we go back to what we did in the lecture, we had the same result without using Lagrange multiplier. I'm going to end this video here. Second video, we will look at a few more examples and a slightly more complicated scenario where there can be more than one constraint. So that's it for this particular video.